So we have started the recording, and today we have Wen-Yuan from King's College. So Wen-Yuan is currently a distinguished postdoc at King's, and he did his PhD in Munich University. Ramesh, can you mute? Let me ask everybody to mute themselves. So we have Wen-Yuan, who is currently a distinguished postdoc at King's College. He did his PhD from Munich University on studying false vacuum decay, on developing some very formal and powerful techniques to study such behaviors. He did his undergraduate studies from Lanzhou University in China, and thereafter he has been based in Europe for a very long time. So his major research interests are in studying phase transition in the cosmology and looking for a signal of those kind of things in the gravitational waves, strong CP problem, non-equilibrium QFT. And today he will talk to us about the recent work that he has done on the absence of CP violation. So let's welcome Wen-Yuan, and let's hear from him.
Yeah. So thank you very much, Cora, for this invitation and also for this very nice introduction to me. And today I'm very happy to be at the HEP to discuss our work. And I'm sorry that I cannot present my talk in person, but hopefully I think I hope we can have some good discussions. And today the title of the talk is the absence of CP violation in the strong interactions. So this the title is kind of bold because this is not the usual the common knowledge we had before, and the work is based on this paper, so published on PRB, and here are my collaborators. The first one is a postdoc at Odense, Juan Cruz, and the second one is Björn Gavish, who is a professor from the Technical University of Munich, and the third one is Karl Tamit, who is also a faculty at the Mainz University. So here before I give the talk, I would like to say that if you have any question, please interrupt me at any time, because I really want to, especially for the students, I really want you to follow step by step. So don't be shy to ask questions. So this is the outline of this talk. I will first discuss or review the enterprise problem in QCD, actually, in particle physics, and then also talk about the chiral anomaly and the BPST instantons, because they are basically the solution to the enterprise problem. And then once we solve the enterprise problem, we actually get a new problem, which is called the strong CP problem. So in this second section, I will discuss what is the strong CP problem. And here, this is the third in the third section is the center section, where I will discuss some technical calculations of the fermion correlation functions in the QCD theta vacuum, and there I will show you that how one can get a different result where there's no CP violation. And then after that, I will give some comments because this is really a very different conclusion compared to the researcher. So there should be many questions, and so here I give some comments regarding the frequently asked questions. And finally, I'll give my summary. So let's start with the enterprise problem. Before talking about the enterprise problem, I would like to give some very basic introduction to the spontaneous symmetry breaking. with and without explicit symmetry breaking. So here we have an example. Here we have example of spontaneous symmetry breaking without explicit symmetry breaking. You see that if you have a potential for a scalar field, and here the potential has a perfect U1 symmetry. Okay, so the theory has a symmetry, but because the potential minimum is not as a region, so when you study your theory, you have to choose a vacuum state. So here, for example, if you choose a vacuum state here, the blue ball here, and then we say that the symmetry is broken by the vacuum state. So this is why we call it as a spontaneous symmetry breaking. And now with this vacuum state, you see that there's a direction around the blue line, which is flat. Essentially, this is the broken symmetry direction. So this means that fluctuations or excitations along this direction give you massless particles called Goldstone bosons. Of course, you also have the excitations along the radial direction, and which give you massive particles. And we are interested in the Goldstone bosons. Now, on the right hand side, on the right, you actually see slightly different picture. Here we tilt, the potential is tilted, and then now, so this actually explains the spontaneous symmetry breaking with an explicit symmetry breaking. By this, I mean that the U1 symmetry is not perfect anymore. Now, if you have the minimal, if you find the minimal, and then the excitations around the blue line is not perfectly flat. So in this sense, you have the pseudo Goldstone bosons, which means that these particles have a tiny mass. Now, from this picture, you see that the mass of the pseudo Goldstone boson depends on how much the symmetry is explicitly broken. The reason I talk about this because in QCD we have the similar phenomena where we have the chiral symmetry breaking. Now, before we discuss chiral symmetry breaking, I would like to discuss first the symmetries for QCD. So let's start with the QCD Lagrangian. At the moment, there's no topological term. So this is Yang-Mills action. The Yang-Mills Lagrangian for the gluon fields, and this is the Dirac Lagrangian. And if you consider massless limit, also called chiral limit, then you actually have the symmetry U3L times U3R. So these are symmetries. So are symmetries related to the rotation in the gauge group space. Here you can understand this from this explicit expressions for the rotation. For example, you have 8 generators for SU3 and 1 generator for SU1. And here you have, because we have left-handed fermion and a right-handed fermion, so this you have 2 copies of U3 symmetry, so U3L, U3R. But we can also decompose this group into the vector ones and the axial ones. So the vector ones, the vector rotation means that you rotate the left-handed fermion and the right-handed fermions in the same angle. Okay, and the axial rotations means that you rotate the left-handed fermion and the right-handed fermions with opposite angle. So in this case, you get SU3V vector, SU3 axial, and U1V times U1A. Okay. So far so good. And now, if there's a chiral symmetry breaking, meaning that the quark condensate is not vanishing. So all the axial symmetries are broken. We are left with vector symmetries. Now you see that actually as I said, there are 8 generators for the SU3A and 1 generator for U1A. And from the discussion we just had for the spontaneous symmetry breaking, we should actually expect 9 pseudo Goldstone bosons. So by pseudo Goldstone here, because the symmetry or the symmetries are not exact. Actually, the axial symmetry are not exact because you have you have a mass term, but still you should have the pseudo-ghost bosons. And indeed, we have 9 mesons, which could be identified as 9 pseudo-ghost bosons. So in this meson, well, here, except L prime is all these mesons are called meson octets, but the L prime was thought to be the pseudo-ghost boson corresponding to the broken U1 asymmetry. The problem is that the L prime is heavier than expected. So this is the so-called U1A problem or L prime problem. So well is a nice pseudo-ghost boson. Well, the solution is very simple. So because this symmetry U1 asymmetry has an additional explicit symmetry breaking from chiral anomaly. So here you consider the chiral current, and the divergence of chiral current is given not only by the mass term. The mass term, of course, breaks the U1A symmetry, but also you have an additional term which is topological. So this means that there should be some mass enhancement for the L prime, due to the chiral anomaly. Now the question is that does this anomalous term vanish when integrated over the whole space-time? Because this is topological, right? And the answer turns out to be that they are not vanishing globally, because there are some solutions, actually instanton solutions, which contribute to non-vanishing anomaly globally. And this is an expression for the BPSD instantons. We also have the BPSD anti-instantons. Well, you just replace the so-called Hooft symbol by eta bar. But here I do not want to spend time discussing about these symbols. I just want to show you some plots for the instanton solution. For example, if you consider the field strength components to 1, and 3 is the label for the generator for the in the gauge group. This quantity is of course gauge dependent, but here here you see the basically the plot represents the size or actually the shape of the instantons. So away we have some radius of the instantons characterized by the rho. Here in the plot I set rho to be 1, so it's roughly around 1, and away from 1, the radius 1, then the field goes to is just vanishing. On the right hand side, you see we show the quantity gauge independent quantity, and then again you see that roughly rho equal to 1 is the radius. Well, as I said rho equal to 1, but for general rho you should have the different radius given by the value of rho. So the real resolution to the U1 problem is that there is an additional explicit symmetry breaking of axial U1 symmetry by instantons. And now, if you consider instantons, then you can get an effective Lagrangian. From this term, this is called a top vertex. And then this term, as you can see, this term explicitly breaks U1A symmetry. Now we have solved the L prime problem, but still this term actually introduces a new problem, namely the strong theory problem. And we are now going to discuss the strong theory problem. Is there any question now so far? Okay. If there's no question, we are.
Yeah, hi. I have one question. What is gamma in your effective Lagrangian?
Oh yes, gamma is some coefficients. If you you need to calculate, you can obtain from the instanton calculations. For example, it is related to the functional determinants. For example, the Dirac operator. If you calculate the fermion correlation functions, you have some functional determinants. Well, so this is some quantity I do not one can obtain from the more fundamental calculations, but here you just take it as a coefficient.
Okay. And theta? Is that
Theta
just
is
a theta angle? UCD theta angle?
Theta, yeah, exactly. Theta is the topological term. Yeah, exactly. I will introduce more about this term. So theta is theta here is a free parameter, basically. But yeah, later I will discuss more about the theta parameter because it's actually related to the theta vacuum in the QCD.
Can you previous slide for like 2 seconds? I missed.
Say again,
show
sorry?
the previous slide. Can you just show the previous slide?
Yeah. This one?
Yeah. So okay. Yeah, that's fine. Thanks.
Okay. Thanks. Now we are going to discuss the strong field problem. So to understand the strong field problem, we have to first understand the QCD vacuum structure. And now, if you for vacuum state, we need to consider zero energy field configurations. And then these configurations require the gauge fields to be pure gauge. So essentially, the gauge potential takes this form. Now, if you assume the U parameter, the U function approach constant at infinity, I mean on R3, then essentially the space R3 is compactified to be a sphere, a three sphere, right? And here we consider the SU2 gauge group for simplicity. And then here we then with this condition we then have the map S3 to S3. So this means that you have some topological structure, and they actually give you from this map you have some so-called Whiting number. So on the special surface, all the zero energy field configurations are characterized by the Whiting number, by the homotopy class of this map, right? And this is actually Whiting number. Wow, I should not call it Whiting number. I should just call it the Chern-Simons charge. So all these quantities, integers, actually given by the integral of the charge density and K naught, and K mu is the Chern-Simons current. So you see that actually all these zero energy field configurations can define different free vacuum. So given by the Chern-Simons charge, but actually this free vacuum does not satisfy the cluster decomposition principle. And actually the true vacuum is really defined as the superposition of the free vacuum. And then here you have the parameter theta, right? So this is called the theta vacuum. So at this point, there's a question: what are instantons? So instantons, physically speaking, they only describe tunneling processes between different pre-vacuum. And then if you calculate the correlation functions in the theta vacuum, then effectively you introduce a new term in the Lagrangian. So this is the theta parameter we just discussed. Now you see that how this topological term is derived from the theta vacuum, but actually from general principles, this term is gauge covariant. So there's no reason to discard it. I mean, even we do not know about the theta vacuum. So we should consider this term at the beginning for the QCD Lagrangian. And so you have a 3 parameter theta. Now, Now with this Newton, and if you integrating out the instanton effects, we finally get the effective Lagrangian of the vertex. And this is something we are going to discuss in detail. But what I would like to say is that the phase here is very important, and with this phase minus I theta, we have the strong free problem. And why? So here I'm going to show you why this phase causes strong free problem. So in general, for the diagnostic, you also have some chiral phases, right? So for U park and D park and S park, you have phases. Now you have to compare the phase in the term of the vertex and actually the deeper by side, basically. So you see that there's a minus side difference here. So if you carry out a chiral rotation, or actually this, you can identify this as field redefinitions. Then on this rotation, then all the angles in the diagnostic plus 2 beta I. You see, plus 2 beta I, but actually the theta minus will be deduced by the sum of beta I, 2 beta I. So this means that all of the phases, either these phases in the diagnostic or the phase in the topological, so total vertex, the vertex can be removed by this field redefinition. But however, this invariant quantity is called theta bar. This cannot be rotated away. Right? So if theta bar is not vanishing, then you have the strong free problem. So from the experiment on neutron electric dipole moment, then we actually constrain theta bar to be smaller than 10 to minus 10. And this is a Weissen's problem. So why this parameter, which should be expected to be order 1, so small, right? So there are 3 possible solutions. Here you see we have we have chiral rotations for all 3 fermions, and if one of the fermions quarks is massless, then we have freedom to rotate for that fermions, right? For that quark, and then you can rotate away the theta bar, the angle. But now this possibility is excluded. And second possibility is that we promote the theta bar to be a dynamic field. This is actually based on the vacuum energy for the theta vacuum is actually proportional to cosine theta bar. Well, if theta bar is not a dynamic field, it's just a parameter, then there's no reason that we should take theta bar to be 0. But if you couple somehow theta bar couple with another field, let's say scalar field, and then as a whole dynamically, the value of theta bar will be relaxed to the CP conserving point. As this is essentially the Petrochem mechanism. Now, there's actually a third possibility. So, if the phase in the top vertex is changed from theta, well, minus theta to plus the sum of the phases from the diagnostic, then again you see that you can rotate the chiral phases in these 2 terms simultaneously, and there's no CP violate. Right? Now the question is that well, this is our result. The question is that how and why we can get this new form of the Hooft vertex, and if this is true, then what's wrong with the standard result? So this is very important, and this is actually well, the Hooft result has been studied for so many years. So you must want to know what's wrong with it, right? Now, before we discuss how can we derive this form of the top vertex, then I would like to give you a quick argument why this form is possible. So the theory is not invariant on the axial U1 symmetry. Means that if you perform chiral rotation here, then the Lagrangian is will be changed. However, if you change the parameters, the alpha, for example, the phase in the diaphragm and also the theta simultaneously, this is called a sphere transformation. You can take these parameters as a sphere. And then again, the Lagrangian is invariant on these total transformations. Now, the standard form of the vertex is actually invariant on these transformations. But actually, you can see that this new form is also invariant on these transformations. So there's no argument in favor of the standard form by the selection rule. And yeah. Now we are going to decompute the fermion two-point functions carefully, and this is going to be a little bit technical. But in the calculations, we will consider only one flavor for simplicity. Now, we are going to calculate the fermion coherence functions in the theta vacuum. This is a picture why we can obtain the standard result, and why we also, so why we obtain the standard result, and why we can obtain a new result. So we are going to calculate the correlation functions using path integral, and this is a plot for the path integrals. We have many passes, and we have to sum over all passes. So when we apply this to field theory, and then the field configurations falls into different topological classes. This is our field configurations in four-dimensional Euclidean spacetime. Okay, and now in each topological sector here, the different dividing number, so there's actually alignment between the chiral phase in the diaphragm and in the top vertex. But if you sum over all these topological sectors, and then we will see by our eyes that there's an interference among these topological sectors, and then you get the standard result. However, if you take the Euclidean spacetime to be infinity before summing over different topological sectors, there's actually lots of interferences, and then you get the new result. So this means that still in the final result, we still have the alignment between the chiral phases in the diaphragm and in the top vertex. Any questions so far? Okay, so let's go. So now we start with the Euclidean Lagrangian. We have topological term here. Notice that there's a difference coefficients between the topological term in Minkowski spacetime and the Euclidean spacetime. And we are interested in vacuum to vacuum transition amplitude. And essentially, so in general, this transition amplitude involves the vacuum wave functional. For example, here, I mean, this is the example for the vacuum wave function. So as we have a minimum and minimum, you should have some weight. Well, so wave function picked on the minima, but still is non-vanishing away from the minima. So, but however, the theta vacuum we have discussed is that we have the wave function is picked. Well, it's not picked; it's just a delta function around the minima. But just and then it is vanishing around the minima. So if you really want to calculate the vacuum to vacuum transition amplitude, you are really concerned with this functional, the wave functional. But in order to avoid this, you can take the time Euclidean time to infinity project on the vacuum, right? So in this case, we obtain the position function. Here you take the omega, the 4-dimensional space-time, Euclidean space-time to infinity, the volume. Okay, so this is very important because the limit actually appears inside the passing square. Now, precisely because infinite space-time volume, finite action of this quantity requires the field strength to be 0 at infinity, so that actually the gauge field approach the pure gauge at infinity. So here the infinity is, I mean the infinity of the 4-dimensional Euclidean space-time. Okay. And again, this gives you homotonic classes for this map, F3 to F3, and this gives you Widen number. We also mentioned this map, but there we were discussing the zero energy gauge field configurations on the special slides. So it's actually on R3. Now we have the position function.
I had a quick question. So
yeah, please.
this gamma, this capital gamma that seems to be kind of crucial for your calculation.
Yes.
That was the object that was computed by, there is this this instanton gas calculation of Hooft from the old days. So I think that object is computed essentially by Hooft in his first paper itself, right?
Yes, that's right.
So, and the claim is that is not correct. That's not somehow because of this order of limits. That's your claim, right? Just trying to understand the precise statement.
Yeah, well, we are not saying that the gamma is not correct. We are saying that the phase.
The extra theta. Yes, that's right. The combination is the theta is changing, so the gamma gets compensated.
Yeah. The gamma is actually does not depend on the phase. So we are not concerned with this real parameter.
Right. I understand. Instead of theta, you have a combination that is coming from the chiral rotations of the masses. That's what you have for the theta. Instead of theta, you have that. That's what it's stating.
Yeah, that's right. Thanks.
Thank
you. Okay, so we have this position function, and then we are going to calculate this position function using the method of steady descent. There are two steps. First, you find the stationary point. We already have this stationary points. They are BPS instantons. Well, in principle, you also need the solutions for general Widen number. BPS instantons are just solutions for Widen number 1 and 1 minus 1, right? But we are going to use the dilute gas, dilute instanton gas approximation, so that you are not we do not care about exact solutions, means the general Widen number. And then means the station points, you expand about the station points. So in this case, you partition your total partition function into a sum over the nu. And the nu is a partition function with fixed Widen number. Okay. And so in the literature, there are two different order of limits. You see, this is the left is on the left is actually the standard one. You first calculate the nu in finite volume omega, okay? With ad hoc boundary conditions, you just let the gauge field to be pure gauge on the boundary. And finally, you sum, and then you sum over nu. After that, in the end, you take omega to infinity, okay? And the second one is that we calculate the nu with infinite omega, and then we sum over nu. So this is a different order of taking limits, right? So if these two different procedures give you the same result, then there's no problem. I mean, then this means that these two procedures are communicated with each other. But we found that the second procedure gives you different results. So this is why we have to be very careful, right? And here there's a very rough argument why the second procedure is correct. So if you use the first procedure, And then for each z nu, I mean each z nu is kind of symbol, left symbol. Well, left symbol actually means the strips that descend contour, right? And because you have fixed boundary conditions, basically for finite omega, then each symbol are not connected. Well, because they have different boundary conditions. There's no continuous transformation between one contour to another one. And you may expect that if you take omega to infinity, then finally all these lines will be connected at infinity of the infinity of the action. This is not sure, but because as I said, because these two procedures do not give you the same result. So probably if you take the omega to infinity this way, then you do not get a connected contour for the original contour for the passing interval. But if you look at the second procedure, all the contours, the nu, they are connected at infinity, right? Because it take omega to be infinity already, then calculate the nu, and then the omega is infinity, so the final action requires the gauge field configuration to approach pure gauge at infinity. And then if the gauge field configuration is not pure gauge at infinity, then you give you the infinity Euclidean action. So this, in this procedure, you get a connected contour for the passing integral. Well, this is still very rough. I'm not trying to be very rigorous about this argument based on Picard left theory. I just want to give you a taste of it. Now, let's do some calculations. We are doing well. We are using the dilute gas approximation. Means that for generating number nu, we simply take n instantons and n bar anti-instantons. Then nu is just equal to n minus n bar. And then now when you calculate two-point functions, then you first calculate the two-point functions, means fixed nu, right? And here you take omega to infinity. Well, this is how to say it? This is vacuum partition function, so normalization. Sorry. Now, here you see, so when you calculate the two-point functions for fixed nu, you have to also know the Green's function first for the field configuration means n instanton and n bar anti-instanton, and this is actually given by the vacuum Green's function. You have away from the instantons, then the field configuration is basically vacuum, and then you have this part. And near the instantons or anti-instantons, the contribution actually are dominated by the zero modes. So this is why you have these forms. Now, so for the coherence function in the neural topological sector, the final form is turned out to be this form. I skipped many details, but here, because the details are not really well, our paper does not have any concerns about our details, the calculation details. It's only about the order of limits. So you should, I think you can trust at least the calculation details. So there's no problem for that. So from here, you see, in this form, you still need to sum this and bar with this constraint. But already you can see the alignment between the diagnostic, which appears in the vacuum Green's functions, sorry, the free Green's functions, and also appears from the top vertex. This appears in this piece. So from the free Green's functions, we have chiral phase. You see, this is our chiral phase, E to minus I alpha gamma phi times PL plus PR. And here, this is the chiral phase from instantons contributions. And again, you see that if you take this phase to the denominator, then you have E plus I alpha. And this is, again, this is also, you have E plus I alpha PL, because gamma phi operating on PL gives you minus sign, right? So this is, you have E plus I alpha, and here again, you have E plus I alpha. So for the left-handed fermion and the right-handed fermions, we have the same phase. There's alignment between in each for fixed nu. Now, below we are going to show that if you take omega to infinity after the sum over topological sectors, then you get the misalignment after the sum. Now, if you take omega to infinity before the sum over topological sectors, then you get the alignment. I mean, the alignment persists after the sum. This is really the center of our paper, the center of our argument. Now, I will show you how to get the standard result. Now, if you keep omega,
I have one more. I have just.
Please.
So, so the way typically when we compute this, like this, let's say neutron dipole moment and so on. Like for instance, in Sretnicki's book, the way you do that is you first argue that there is an invariant theta, which is basically the determinant of the quark mass matrix times e to the minus theta or whatever of the theta angle. So then you call that your theta prime, theta bar in your notation. And then you basically write down a chiral Lagrangian. And in the chiral Lagrangian, this is the mass, m bar that goes in, which contains this theta bar. And then at the end of, then you do a perturbative calculation and you end up finding that the neutron dipole moment is proportional to theta or whatever. And then you argue from phenomenology that it is extremely small. So I'm trying to understand where your calculation. So in that calculation, for instance, it just seems very intuitive. I mean, there might be some formal path integral thing that is going into it. But it's from the calculation, it just seems very straightforward and intuitive in some way. And I'm trying to understand where this particular technicality is going into that calculation. You know what I'm saying? Like,
yeah, sure. So I will discuss chiral perturbations here later. And here we are still trying to derive the form of the Hooft vertex. But after that, we will talk about the chiral perturbations here, which is more directly related to neutron dipole moments.
Right. So, but what I'm saying is that okay. Anyway, go ahead. Yeah. So I think my point in some sense is that, like, once the sort of the formal argument for the theta bar is in place, it seems natural in some sense to put that into the chiral Lagrangian. So I'm saying that, like, somehow I understand the technical statement that you're making that the order of limit matters. I mean, I didn't follow all the details, but at least it's plausible that there is an order of limits issue in this calculation, the way, in terms of this capital gamma term. But I'm trying to reconcile that with this, this calculation is there in Sretnicki, for example, so that calculation, how would one reconcile that is what I'm trying to kind of see. Yeah. Anyway, I think so you can answer that later at the end of the thing if you like.
Exactly. We may come to this discussion later.
All right. Thanks.
Yes. And so here we are still calculating the two correlation functions, and here I show you how one obtains the standard result. Or by standard, I mean the Hooft result. So if you take omega to be finite in each topological sectors, then essentially there's no difference between these two sums. You sum or n and bar independently. And then if you sum so this is the nu. You have kappa, this quantities, and then this finally gives you e2 minus 2 kappa omega. Kappa is function related to the functional determinant. The fermionic functional determinant. And then here you see that this is web pure position function, and then you see how the theta bar dependence in the energy function in the energy terms, because you can defer. You can actually infer the energy from the position function. And this is for the two-point functions, and in the two-point functions you actually get the misalignment if you do the sum.
well, this is here. From here, you see that there's a again. This is minus I alpha gamma phi, and then here from this term you get E I theta gamma phi, and then this is you get the misalignment between these two faces. And then unless theta equal to minus alpha. And then this gives you the strong speed problem. But here, if you first, if you take the omega to infinity before summing over nu, then you have to do the sum within fixed new topological sectors. And then this is our, this is your result. This is your result. And then you see, so the two-point functions, finite two-point functions, is really you still have to sum over nu. And now, if you take omega to infinity first, then there's an identity. All the modified Bayesian functions are the same, are equal to each other. So in this case, all these modified Bayesian functions cancel, and also these terms are the same cancel. So finally, you get. You see, this is essentially kind of a lot of interferences between different topological sectors from this quantity. And then finally, this is your result. You get the same. This is the phase in the from the diagram, and this is the phase from the instantons, and then they are the same. This is why you get the alignment. Now, okay, so maybe this comes to the more interesting discussions regarding the kernel provision theory. So for kernel provision theory, you have the term for the, well, U is actually the quark bilinear field, and then now these terms are actually from the instanton effects, and it's really very important that you have the what is the phase in these terms, and from the top, the standard form of the top vertex, here C is really should be theta. Well, here we consider M the diagram still has the color phases, the alpha, right? And then from this one you can okay, so the angle C in this term, the crucial point is that this phase affects the orientation of chiral condensates. So in many calculations, if you see is equal to theta, then the chiral condensate lies on the real line. I mean, so this is actually can be obtained from this relation between this is the phase for the chiral condensate, and also you have some the chiral phase in the diagram. But you see the relation C, the phase C enters in this relation. So this is very, very important. So finally, you get the effect. For example, you get one term in the effect of Lagrangian, which describes the decay of eta pi to pi pi. For example, if C equal to theta, then this you get some CP violating process. But if, as I said, so the phase C, it really depends on form of the top vertex. And in our result, C should be alpha minus alpha bar, minus alpha, and then this cancels. Finally, you get so this term vanishes. So you see that why is the phase in the total vertex affects calculations in the chiral perturbation theory. And actually, after I have a backup page and discussing more about this, we discuss the ballooning operator. I think you are more familiar with the ballooning operator and why. Again, in that calculation, we still assume that the chiral condensate, the orientation of the chiral condensate lies on the real line. But actually, really, if you follow this relation, then you see that the phase is can affect the chiral condensate. Now, another question is that now you see that because there's the coherence between different topological sectors, so somehow when you calculate the quantities, it's kind of
effectively is the same when you calculate the correlation functions in a fixed Widen number. Then you may ask that, okay, so how from these calculations you should get some vanishing global topological scalability, right? Because omega is going to infinity, while this is some fixed number, and then however from lattice QCD we obtain some finite topological scalability. Now, why? How do you explain this? Well, our explanation is that if you consider a fixed Widen topological sector, and indeed this quantity, the global quantity is vanishing. However, if you consider local, for example, the local topological scalability, for example, in this volume omega 1, and then the delta n1 plus delta n2 is fixed. Delta n is fixed, but actually delta n1 and delta n2, they are not fixed. Okay, and then you have fluctuations in this local quantity, in this small box, and then finally we actually did this calculation in our paper, and we obtained the topological scalability. The local quantity in this volume is given by 2 kappa, and this is in agreement with the QCD simulation. Here, before I give the summary, I also want to discuss one page about the ballooning operator. Again, here, then, okay, this is the story about how people obtain the CD violating Lagrangian. So you first started from the fundamental Lagrangian, right? So, and then you have the theta term, and then you perform the chiral rotations to remove this term, and then you just have this Yamil's action, sorry, so Lagrangian, and you have Dirac mass term. Now the phase in the Dirac mass term is theta bar, because you already do the rotations. Now, naively, you can analyze chiral synchrotron breaking based on this term, right? So based on the classical analysis, and then you can get the CB violating Lagrangian I theta minus I theta bar times this term. And if theta bar is not vanishing, then you get a CB violation. However, you cannot analyze the chiral synchrotron breaking only based on this term, or actually you cannot based on this term classically. You have to, otherwise you have to ignore the instanton effects. So the real way to analyze the chiral synchrotron breaking, or actually the phase in the chiral condensate, is really you need to start with the Lagrangian, for example, this Lagrangian, and also with the vertex term. And then if you do that, so again you get a vanishing CP violating term. So what I mean is that you really need to so you really need to analyze the chiral synchrotron breaking based on this term. You cannot ignore this term. And the phase appearing here can affect the phases in the chiral condensate. And then, I mean, it's actually national. If this phase is replaced by plus alpha bar, then you can remove all the chiral phases simultaneously, and then almost immediately you can see that there should be no CB violation. Now this brings us to the summary. So in our paper, we constructed the fermion Green functions in BPSC instantons with general complex space, and also we observed alignment between the chiral phases in the Dirac mass term and also in the top of the vertex term for infinity space-time volume. So here, this is really the importance of how you take the order of limits. And then in our paper, we also, all the discussion in this work is based on the dilute instanton gas approximation. But in our paper, we also give a very general analysis based on the cluster decomposition, and we get the same results. Thank you very much for your attention.
So let's thank Wen-Yuan for the wonderful talk. So any questions?
Yeah, I did have one question. These instantons typically are the fields go all the way to infinity, right? So can you comment on how the cluster decomposition is going to work? So
I didn't get it. Can you say it again?
we understand how cluster decomposition works for massive fields because the correlation function between two massive fields falls off like an exponential where the fall off is determined by the mass, right? And so therefore we understand how cluster decomposition works for correlation functions of massive fields. But for instanton fields, because they are long range fields, how does one understand how does one get cluster decomposition to work? For example, we know that it is very tricky and very subtle to get cluster decomposition to work in the case of QED, for the case of the photon field, right? You can get it to work for the electron field, but it's much more subtle for the photon field. Similarly, for gauge fields, non-abelian gauge fields, where the fields are long range, how would you get cluster decomposition to work? That's sort of my question.
So I'm not actually very familiar with what you said, but I think, for example, in the QC instantton calculations, so once the cluster decomposition, when we go from the pre-vacuum, and we calculate by fixed gauge configurations, which give you the transcendental charge, a fixed transcendental charge. But if you take a superposition for the pre-vacuum and then you go to the theta vacuum, then this theta vacuum actually satisfies the cluster decomposition. So I guess so I'm not totally sure the discussion you mentioned, but I guess if you go from the field configuration, fixed field configuration to some space, like it's a superposition for the for different instantons. Well, actually, then actually you can satisfy the cluster decomposition pretty simple. Somehow, for example, if you calculate the correlation functions for a theta vacuum, then there's no problem with the cluster decomposition.
Okay, so I think I understand what it is. You're taking correlation functions of the massive quark fields. Is that right? You're looking at the correlation functions of the form psi bar x, psi of y, and so on, where psi is a quark field for a massive quark. Is that right?
Psi is massive quark, yes.
Sorry? Psi is a massive quark, right?
The psi is quark, and you have a master.
And you have, so it's a massive quark, right?
Yeah.
Okay, yeah. Then I think I understand. Yeah, thank you.
But I think your criticism is actually of the dilute gas approximation of instantons.
Yeah. I was going to say that.
Yeah. So I don't know. So I don't know whether there is a real counter argument to that, because people have made this.
We will have to. I would like to see their paper actually to understand better. But it seems very interesting, the work.
So I had one. So for instance, I mean, the standard computation of this neutron dipole moment calculation, usually, for the one that, for instance, I mean, the one that I have seen is the one in Threadnicki, for example. There is no determinant U type term. What you instead have is basically the nucleon, and then there is the pion Lagrangian is sort of kind of like the mediator, so to speak. So there is no analog of dit U there. Here you are doing the calculation for the eta prime directly, so it looks like everything is in the Meson language. So yeah, so it would have been nice to kind of it may be a useful thing, or maybe you have already done it, to kind of frame this calculation in the neutron language, I think, because I think it'll be good to see where exactly the e to the I psi is going in.
Okay, yeah, I see what you mean. So you mean it's a neutron dipole moment system? No, this term is not involved.
Yeah, so because in the
Um,
the typical calculation of the dipole moment, for instance, it's a nucleon calculation. So you have basically you introduce the nucleon, nucleon basically doublet, like let's say, and then you have this pions as intermediaries, and that's the kind of chiral Lagrangian theory where they calculate. So and here, because of which there is no determinant U term.
yeah,
So,
well,
but I'm sure there is some way in which it is showing up, but it will be nice to kind of clarify that context, because there it's not, kind of seems like in the standard calculation, it just looks like you're putting in the quark masses with this theta, the theta bar term. And so the calculation seems sort of compelling there. So it will be nice to kind of understand where exactly the problem is going in there.
Yeah,
anyway, I mean, it was nice talk. I mean, I did not fully follow the technicalities of the infinite volume limit, but yeah, seems possible.
Yeah, thank you very much for this comment. I think this is very helpful, and I think we should actually really make this very exact for the people.
I have one more question. Sorry. Will the kind of technology that you used, will it also affect the discussion of confinement deconfinement transition, where you put in where you look at the Polyakov loop? There, for instance, the periodic people study the contributions from periodic instantons that are periodic in the Euclidean time direction. So again, I was wondering whether some of the discussions regarding confinement deconfinement transition would be affected, because you say that what matters is whether you take the limit of the period going, whether you take the limit of the volume going to infinity before or after.
Yeah, well, so yeah, I think this is a good comment, but I haven't studied before, so not sure.
So
I'm not fully sure.
I have a general question, which is kind of a generalization of what what Sachin was asking. Which is that, do you have any signatures of this failure of this infinite volume limit in non-chiral theories? For instance, the theta angle is, there are very good reasons to believe in the finiteness of the theta angle in some supersymmetric theories, but they typically, at least in cases where you really believe the theta angle, but they are like, for instance, in n=4 superangles theory, for instance, there is a theta angle, and the theta angle, I think, is unassailable. I think it is really strong reasons to believe it, but you also do not have chiral fermions. So maybe I think that, so this confinement, deconfinement, taking it more generally, like, is there any setting in which you can see signatures of this tricky infinite volume limit in a non-chiral theory? So in that is the case, I think it will be a good check of some of the things that you're doing.
Yeah. Well, yes, I mean, so this is again looks like a comment to me, because I really have not really thought about it before. The theory you discussed. I think there are many things we need to do in the future to make our argument more convincing to people. And actually, currently we are still working on your Mills theory on a finite volume. I mean, for example, on a torus T3, and you can also consider compare Euclidean time or not. And then there we also find that there's no CP violation. So this is kind of a complementary argument for the discussion in this talk. Yeah, thank you very much for your comment.
So, any more questions? So let's see the chat box if there is something. No, nothing in the chat box yet. So if there are no further questions, then let's thank the speaker and Wen-Yuan and the audience for listening. And So yeah, so we'll be uploading this recorded talk in the CHEP YouTube channel, and whoever wants to listen it again, there will be it's accessible to a wider audience also. So let's thank the speaker, and
Yes, thank you very much.
So thanks to Wen-Yuan because he agreed to come and give a talk, and we hope that maybe sometime in future you can visit us in person.
Yeah,
And,
yeah, it's my pleasure.
Yeah.
Yeah.
Okay.
Thank you. Bye bye.